In this video, I will present an example of how to calculate the value of a series directly from the definition. It will be this one. I invite you to pause the video and try to calculate it, and then continue watching. I want to calculate the sum from n equals 1 to infinity of 1 over n squared plus n. By definition of series, what I have to do is find a formula for the sum of the first k terms and then take the limit as k goes to infinity. And if I don't know what else to try, it won't hurt to simply compute the first few of those partial sums and see what we get from there. Let's do that. The first partial sum, S1, is simply the first term, 1 over 1 squared plus 1, and that is 1/2. The second partial sum, S2, is the first partial sum plus the second term. And this is 1/2 plus 1x, 6, and this comes up to be 2/3. The third partial sum is the second partial sum plus the third term when n equals 3. That is 1 over 3 squared plus 3. So that is 2/3 plus 1 over 12. And this simplifies to 3 over 4. And I'm going to stop here because I think I already see a pattern. S1 is 1 over 2. S2 is 2 over 3. S3 is 3 over 4. I think I can guess a formula here. This is just a guess so far, so I'm going to call it a conjecture. But it appears that for every k greater or equal than 1, the kth partial sum is k divided by k plus 1. It certainly works for the first three. This, of course, needs to be proven. I cannot simply state it. And perhaps the simplest way to do this proof is by induction, because from their definition, the k plus first partial sum can be written as the kth partial sum plus a term. So if I have a formula for the kth partial sum, I can get easily a formula for the k plus first partial sum. This is a standard proof by induction, and it works fine. I won't write down the details. However, I'll notice that to do it this way, I need to be able to guess the correct formula. There is an alternative approach for this problem, even if you are not able to guess the correct formula. Here is a different way to obtain the same result without any guessing. I want a formula for the kth partial sum, which is the sum from n equals 1 to k of 1 over n squared plus n. And I notice first that this denominator can be factored. So I'm going to rewrite it as 1 over n times n plus 1. And this makes me think of partial fraction decomposition. I can split this as the sum of two fractions with simpler denominators. In one case n, and in the other case n plus 1. Now you can use a more systematic way here, but I'm just going to do a little bit of guess and check. I think if we put a 1 here and a 1 here and I subtract, it works because the denominator will be n times n plus 1, and the numerator is n plus 1 minus n, which is 1. Yes, this works exactly. So I have simply rewritten this algebraically. And now, because I am working with a finite sum, I can use all the manipulations we are used to using with partial sums. I can use properties and regroup terms and all that. So I'm going to do exactly that. I have k terms here. Every term is a difference of 2. I'm going to expand and see if some of the terms cancel. And they will. So when n equals 1, I get 1 minus 1/2. When n equals 2, I get 1/2 minus 1/3. And look at what's happening here. I already have a cancellation between this 1/2 and this 1/2. When n equals 3, I get plus 1/3 minus 1/4. And again, I already have a cancellation between this 1/3 and this 1/3. And it looks like almost all the terms are going to cancel. So I keep doing this. And the last term will be when n equals k. And I get 1 over k minus 1 over k plus 1. And again, all the terms cancel. This minus 1/4 cancels with something there. This 1 over k will cancel with minus 1 over k. And I'm left only with two terms. The first term, which was 1, and the last term, which is minus 1 over k plus 1. And this simplifies as k over k plus 1. And this is the formula for sk that I obtained before, exactly the same one. Except that now I didn't have to do any guessing. And also, this on itself is a proof. If I derive this formula this way, it's already proven. I don't have to use induction or anything else next. This is good enough on itself. So either in the previous way, I guessed the formula and proved it by induction, or in this way, using this manipulation, I know what the sum of the first k terms is. Therefore, I can now use the definition of series to calculate the value of the sum of the infinitely many terms is. And I know that the original sum of 1 over n squared plus n from n equals 1 to infinity, is simply the limit as k approaches infinity of the sum of the first k terms. And since I now have a formula for that, I can compute this limit. It's the limit as k approaches infinity of k over k plus 1, and that is simply 1. So we have concluded directly from the definition that this series is convergent and that it adds up to 1.